Hey everyone, welcome to our YouTube channel. Today we are diving into the world of catalysis, where science and magic meet, but without the wands. We will break down heterogeneous and homogeneous catalysts and explore the Haber and Monsanto process. Let's get started.
So first of all, what is a catalyst? A catalyst is a substance that decreases the activation energy needed for a reaction by providing an alternative pathway. The lowered activation energy causes more particles to meet the energy requirements, thus increasing the rate of reaction. Catalyst also remains unchanged at the end of a reaction, meaning that it can be reused.
Types of catalysts. There's two types of catalysts, heterogeneous catalysts and homogeneous catalysts. Heterogeneous catalysts are like that one friend who's always in the corner at the party, standing out because they are different. They are in a different phase than the reactant, like the red picture, that the catalyst is in a solid phase while the reactant is in a liquid phase. On the flip side, homogeneous catalysts are like in the same phase as the reactants, like everyone at the party being in the same room dancing with the same music. You can see this from the blue picture.
So you may now wonder, what is a heterogeneous catalysis? A heterogeneous catalysis is a reaction which uses a heterogeneous catalyst, which, as mentioned before, is a catalyst that is in different phase to the reactant. For example, a gaseous reactant and a solid catalyst. A heterogeneous catalysis occurs in different stages. First, the reactant will diffuse into the surface of the catalyst, which it will then get absorbed into the catalyst. After it is absorbed, an intermediate will be formed. The reaction will then commence until the product is formed. Then the product will detach from the surface of the catalyst, which the process then repeats.
Now let's talk about homogeneous catalyst. It's the catalyst in the same phase to the reactant. You can see in the left pictures. The first one, which the reactant and the catalyst are both aqueous, and the below picture, that the catalyst and then the reactants are all gas. The aqueous transition metal ions are the most commonly found homogeneous catalysts because they have variable oxidation states. You can see in the periodic table below, these elements are all metal.
Next, we're going to be talking about the Haber process. Haber process is an industrial process developed by Fritz Haber and Carl Bosch during World War I. The process is used to produce ammonia from nitrogen and hydrogen, utilizing iron as a catalyst. The process is separated into multiple steps. Firstly, nitrogen is extracted from the air, which is then mixed with hydrogen, which is produced from natural gas. The reaction is then driven with a 200 atmospheric pressure and 400 Celsius condition. After the reaction occurs, ammonia is produced, then the iron catalyst will regenerate back into its original form. The uses of Haber process includes fertilizers, making explosives, nitric acid production, refrigeration, and many more. The impacts of Haber process is that it revolutionized agriculture by enabling large-scale production of ammonia-based fertilizer. Its reliance on a catalyst allows the reaction to proceed under more feasible conditions of temperature and pressure, making it one of the most important industrial processes. Next, we're going to be talking about the case study, which in here is of Robert, an engineer who contributed to the Haber process. So, for background, Robert was a British engineer who played a very important role in the development of Haber process. He was born in Mauritius and later worked together with Fritz Haber. The challenges faced during this era is that at the start of the 21st century, the world was facing an increasingly high demand for ammonia, which is used to make fertilizer and explosives. And at that time, there was no method for synthesizing ammonia that was efficient enough to meet the high demand. The solution to this was that Robert collaborated with Fritz Haber, who had already developed the basis of producing ammonia from nitrogen and hydrogen by using high temperature and pressure. He did this by designing key apparatus that allows for precise control over temperature and pressure, such as high-pressure gas pump and a reactor system.
Next up is the Monsanto process. No, it's not about Monsanto's secret recipe for cookie, though that would be a great story. It's actually a method for producing acetic acid from methanol and carbon monoxide. This process uses a rhodium or iridium-based catalyst complex with iodine. You can see in the diagram the reaction step in the left side. Firstly, formation of metal carbonyl intermediate, then the intermediate reacts to form acetic acid. Ta-da! And the catalyst is regenerated during the reaction cycle. The uses: it is used in various industries, from industrial and agricultural applications, consumer products, pharmaceutical, and much more. The impact: it improves the efficiency of acetic acid production, leading to cost reduction and more advancements in technology. Here's a case study: the Cavida process for acetic acid production from the Monsanto process. So here's the background. Acetic acid is an industrial chemical with a global demand of around 6 million tons per year. This process had limitation though, in terms of efficiency and cost. In response, BP Chemical developed the Cavida process in the 1990s, which utilized an iridium-based catalyst to significantly improve productivity and reduce costs. The problem: the Monsanto process used rhodium catalyst, which was the key method for producing acetic acid with the carbonylation of methanol. However, there are various disadvantages, such as catalyst degradation and side reactions that reduce overall efficiency. Furthermore, it also operated under relatively high water concentration, which increased energy costs for downstream purification. Also, the cost of rhodium, which was the main catalyst, was kind of high. The solution: BP Chemical introduced the Cavida process, which replaced the rhodium catalyst with a promoted iridium catalyst, creating a higher catalyst stability. By the iridium catalyst was more robust than the rhodium, especially at lower water concentration, which allowed for more efficient operation. It also improved productivity. The Cavida process increased can throughput, allowing existing facilities to produce more acetic acid without major expansion. Lower concentration in the reactor meant less energy was needed for distillation and purification, leading to overall lower operating costs, thus reducing the energy consumption too. Lastly, the process resulted in significantly fewer byproducts such as propionic acid and carbon dioxide, reducing emission and simplifying purification steps. The first commercial plant using Cavida process was brought online in 1995 in Texas City, USA. Following its success, other plants in South Korea, the UK, and Malaysia adopt the process. By 2000s, the process was widely recognized for its environmental and economics benefit. It reduced energy consumption by 30% compared to the Monsanto process, while also cutting CO2 emission by approximately 70%, helping our environment healthy.
Next, we're going to be talking about the differences between Haber and Monsanto process. Here's the comparative analysis table, highlighting the differences between Haber and Monsanto process. Firstly, The differences in primary purpose. The Haber process uses synthesizes ammonia from nitrogen and hydrogen, whereas the Monsanto process produces acetic acid from methanol and carbon monoxide. The main reaction for both of the processes are also different, as can be seen on the slide. The Haber process uses nitrogen and hydrogen, making ammonia, whereas the Monsanto process uses methanol and carbon monoxide to produce acetic acid. The catalyst used is also vastly different, with Haber process using iron as a catalyst, whereas the Monsanto using rhodium or iridium complexes with iodine as a catalyst. The reaction condition for both of the process is also vastly different. The Haber process uses a temperature at around 450 degrees Celsius, which is significantly higher than Monsanto's 150 to 200 Celsius. The pressure required is also different. For Haber process, the process requires about 200 atmospheric pressure, whereas the Monsanto process, the pressure usually differs, but it's usually about 30 to 50 atmospheric pressure. The reactant, as said before, is also different. For Haber process, it uses nitrogen and hydrogen, whereas Monsanto process uses methanol and carbon monoxide. The application of both processes, the Haber process is mainly used to make fertilizers, whereas the Monsanto is mainly used for production of various chemicals such as acetates, acidic anhydride, for example. The pros and cons of Haber process. The pros is that it is scalable for mass production, although it requires a factory and high pressure and temperature condition. It doesn't require any more than that, which allows it to be scaled for mass production. It also allows for increased global food production because it is mainly used to make fertilizers, and fertilizers are used to grow crops, which if there is an increase in fertilizers, it will lead to a increase in growth of crops. The cons is that it requires a lot of energy. As mentioned before, the temperature and pressure required to drive the process is quite high. It also causes a lot of CO2 emissions, which is bad for the environment.
Now, here's the pros and cons of Monsanto process. The pros is it high efficiency and yield, which mean the higher amount of products. And the catalyst is extremely durable, meaning it can be reused. On the flip side, the catalyst is extremely expensive and causes environmental concern because of its toxic intermediates.
Here's the reference of our presentation. You can pause or click the link in the description for more information on the topics we covered during the presentation.
Thank you for watching and see you next time. Don't forget to subscribe. Remember, in chemistry and life, sometimes the best reactions are the ones that bring everyone together. Bye.
Bye.